Thank you for the introduction. So I'll be presenting our work on facial relighting with limited zonal illumination. This work is done in cooperation with Yiming Din, Xiaohui Li, and Professor Abhijit Ghosh. So to give a background for our research, current state-of-the-art subject relighting methods are almost exclusively based on having a light stage, which is first proposed by Debevec et al. At the year 2000. A light stage is most commonly used to obtain an array of one light at a time images, what we term OLED images, to brute force the reflectance field. So you get an image-based reflectance representation that can be used for high-quality relighting. So while having a light stage is advantageous, building one is actually pretty challenging. So if you consider the complex hardware and specialized control circuit, it's not trivial to build. It also takes up a lot of space and costs you a lot of money. So building light stage is not good. And like for most people, it's not practical. The question is, can we achieve similar quality results with a much simpler setup, say using a bunch of monitor screens and capturing images with consumer-grade cameras? And with this research, we want to convince you that, well, this is possible, that we can learn a reflectance field of a subject which has an expanded illumination zone compared to the setup that we captured the data with. And of course, everything is learned with the data captured with this kind of practical setups. So before we move on to our method, let's go through some related work of reflectance modeling. So Meka et al. Proposed a unit architecture to predict several OLED images given two gradient images of the subject. And Sun et al. Similarly uses a deep neural architecture to interpolate OLED images captured within a light stage. Note that the previous work done on reflectance modeling all requires data captured from light stage. In their case, they would require a light stage with around 300 individual light sources with multiple high-speed cameras capturing at 60 FPS. So compared to our work, we would need 4 monitor screens and consumer-grade cameras that capture at 3 FPS. So another area of work focuses on single image relighting under passive environment map. So while the end product of these research require only a cell phone, to train such a model, you would still require a light stage. And previous to our work, there are also some researches on relighting that attempts to replace a light stage with more practical setups. So Sengupta et al. Learns to relight a subject under a target screen illumination, while Latas et al. Used a more practical setup to capture the SV BRDF of a given subject. For these methods, they either have a limited relighting zone or they need to assume an explicit BRDF model which limits the relighting accuracy. So can we do better? Specifically, can we achieve full coverage relighting like what you would get with a light stage using zonal illumination captures by, say, training a deep model using the data that can be captured with this kind of practical devices? So to be more specific, we want to learn a deep reflectance model that predicts a set of OLED images that expand the illumination zone of the device, the capture device that we have. The images should be aligned to, say, a reference image of the subject lit under flat lighting, so we can use the data to create a high-quality relighting result. So in order to do that, the first step that we look into is the data capture process. And what we want is a data set with expanded zone of illumination. And what we observe is, well, a single camera can only observe a limited zone of illumination. By placing multiple cameras around this kind of setup and having the subject face each camera during capture, we effectively have different cameras that observe a different zone of illumination. So while a direct OLED sequence capture is impossible, we can get multiple partial OLED sequences with slight pose and like expression variations in the subject. And hopefully this will give us enough information to train a full coverage reflectance model. So another thing we have to deal with is subject movement during capture. What we propose is to capture one full-on image between each full-on image so we can estimate optical flow. So if you have a light stage with high-speed camera, this is usually not an issue because you can align the images with optical flow. With slower captures, the strategy is not optimal because movement between the full-on images wouldn't be linear. What we find more reliable is to try to detect excessive movement instead of directly trying to align all that images to the full-on images. So to detect excessive movement, we estimate the maximal optical flow between two full-ons. If the maximum flow exceeds 8 pixels, we say there is excessive movement. Otherwise, we assume that the OLED is sufficiently aligned with the full-on image. So with this strategy, we can acquire two sets of data. The first set is paired data, where each OLED has a corresponding full-on image. And with our method, the misalignments between these two images would be, say, within 8 pixels. We also get a set of unpaired data where the subject moved during the capture. So we still get OLED images, but we don't have any full-on images that corresponds to these. So in our capture, we find that around 40% of the OLEDs will be unpaired, and the exact amount will depend on how likely the subject is to move. So it takes up a significant amount of data, and that will affect the later design choices on designing a reflectance model. So with the acquired data, the next step is to design the reflectance model. This is a high-level overview. So now I'll go into detail on all the design choices. So for high-quality modeling, the first step we need to do is to deal with movement between the paired data. And to do this, we propose to encode all the images into an 8 times downsampled latent space image using a VQ-VAE. The idea behind this is that downsampling itself will reduce movement. And if we encode all the features into a downsampled enough space, then in a latent space, the movement will basically be negligible. And later on, if we were to train a model that predicts, say, a OLED latent image from a full-on latent, the quality wouldn't be affected by the movement in the actual data set. So while this strategy works, encoding images mean we inevitably will lose some information, especially the high-frequency details that we want to preserve in the relighting. And to mitigate this, we propose to add a skip-assisted decoding into our VQ-VAE. And what it does is, while we try to decode OLED images, we use the multi-scale features extracted from the paired full-on image to provide the high-frequency details in order to reconstruct the high-quality OLED image in the end. So the only issue with this is in the training process, we have to have a way to still deal with misalignments. And to do this, we propose a simple modification of a standard perceptual loss by adding max pooling operation to the extracted features, creating what we call a misalignment-aware perceptual loss. So note that a standard perceptual loss calculates the square distance between the features of images extracted at different depths from a pre-trained classification network. So by adding a pooling layer before calculating the difference, we only compare the difference of the maximum activation in a local area, which is more robust to slight movements and misalignments. Note that the window of the max pooling will shrink as we go into deeper layers since they output lower resolution features. So with this design, we are now ready to formulate our training for the VQ-VAE. For unpaired data, we don't have a full-on to provide the information, so we just train it straightforwardly with the loss function proposed by Meka et al. And with paired data, the decoder is trained with the multi-scale features extracted from the full-on image. And we make a slight modification of Meka et al.'s loss function by replacing the standard perceptual loss with our misalignment-aware perceptual loss. We also don't use the mean square error for training the paired data. So with the VQ-VAE trained, now we can encode all captured images into a latent image space. The second step would be to train a model that predicts OLED images, well, OLED latent images from full unlatent image. So to design this, we should consider some points that the model would need to somehow extrapolate the lighting zone, thus may have to have the ability to hallucinate some details that wasn't directly seen in the data set. It also have to efficiently utilize both paired and unpaired OLED data, because note that we do have around 40% of the captured data being unpaired. So this makes the standard image-to-image translation method not ideal for our task. Instead, we choose to use a conditional generative approach to solve this issue. Specifically, we implement the standard diffusion process. And using a generative approach allows us to use both paired data and unpaired data in the training process. So to recap, our training pipeline looks like this. We first train our VQ-VAE with the skip-assisted decoder. After that is done, we encode all the captured data into its latent space image. Then we train a conditional diffusion model that is conditioned by the latent full-on image and the given lighting direction to produce a latent OLED image. For inference, given a full-on image, we first encode it into its latent space image, at the same time extracting multi-scale features. The latent space image is then passed through the latent diffusion model to create a latent OLED, which can be decoded with the help of the multi-scale features to reconstruct the high-quality OLED image. So here we show the results of our method. The top row are the actual captured OLED images that is present in our dataset. So note that the pose and even hairstyle will vary within the capture because the subject have to move around. The bottom row are the OLEDs predicted from the reference image. So you could see that this subject is never observed in this exact same pose under these lighting directions, but the network learns to create a plausible OLED image given any lighting direction, thus expanding the illumination zone of our physical setup. And with our method, we can illuminate the subject under a full coverage of environmental lighting, like what you can achieve with the light stage. So, play this. So, and by capturing the subject under multiple expressions, we can learn a reflectance model that relights a subject across expression changes. Thus, we can relight a performance capture video of a subject lit just under flat full-on lighting. And to illustrate the importance of expanding the illumination zone, we compare our relighted result versus trying to relight the subject with only limited zonal lighting, or trying to approximate the environment map with Voronoi cells. Note that only our method produced the realistic backlighting effect of the subject lit by the window behind her. And this wouldn't be achievable with Voronoi cell approximations. And the effect is even more prominent in video relighting, where the environment map is changing. So with Voronoi cell approximations, the change of lighting from the back cannot be correctly modeled, while our method can create a smooth relighting video of the environment map rotating. So here we compare the result of our method with the reflectance field of Meka et al. On the right, you can see our method produces sharper specular details and have better textures. We score better at the perceptual similarity scores, but we do note that the structural similarity scores of ours is worse. And this is because that our method is generative in nature, so it will hallucinate perceptually good details, but it may differ from the ground truth. And also one thing to note is that Meka et al.'s method requires 2 gradient images, so you can't directly use their method to extrapolate lighting if you are using a limited illumination device. But we also performed ablation study with our skip-connected decoder and misalignment-aware perceptual loss. Our result on the right, hopefully it's visible on the slides, but our result on the right produces the sharpest details compared to either using the slide pooling loss proposed by Mecca et al. Or not using skip-assisted decoding at all. So now I'd like to address some limitations in future work. We do observe some grid-like artifacts on our predicted OLEDs. So this is like a potential limitation. However, we do note that once you create a relighting, given an environment map, the artifacts usually cancel out. So we believe it's a worthy trade-off because with our method, you can preserve the high frequency details. And also our work currently works only on a per subject basis. So to relight the subject will need to go through the capture sequence and retrain a model that works only for the particular subject. And it'll be interesting if we could, say, capture more subjects and have a cross-subject reflectance model in the future. So to summarize, we present a method for high-quality relighting and OLED prediction with practical zonal illumination setup. To obtain high-quality reconstruction of OLED images, we propose a skip-assisted decoder and a misalignment-aware perceptual loss used to train the decoder. And hopefully, our research provides an alternative path to reflectance research without the need of the light stage. Thank you for listening.